All right, last one from me. I'm just going to go through the exam questions that I set. Again, not practice these, so let's just go with it. I hope I do all right. All right, complete a word equation for the combustion of hydrogen. Combustion just means burning. We do a bit more on combustion of hydrogen and carbon next year. If you burn hydrogen, if you burn H2 in O2, I hope it's not a surprise that you make H2O, but it wants a word equation, so you have to write water. If you write H2O, no marks because it wants a word. Burning hydrogen makes water. Next one, a simple energy level diagram. All right, looking at this, reactants, products. The products are lower than the reactants. There's an exothermic reaction because energy has exited, energy is left. All right, which arrow A, B, or C shows the activation energy? Well, activation energy is from here to here, so that's going to be represented by A. B, what is B? Anybody? Yeah, B is the energy change or the enthalpy change, and C is nothing, I suppose. I suppose C could be the energy released when the energy released from making bonds, because it goes from the top all the way to the bottom. But that's not really anything that we see normally on a reaction profile. What type of reaction is shown? It's exothermic, and how do you know? Give a reason for your answer. Now, it doesn't ask for a reason in terms of bond breaking and bond making. It's just asking you to look at that diagram and say, how did you come up with exothermic? Sorry, you have to write thermic. I'm just being slow here. So, not slow, lazy was the word. How do you know it's exothermic? And you know because the products have got less energy than the reactants. You know, if you then went on to say because energy is has been released to the surroundings, that's fine. But the way that you spot it is because the products have got lower energy than the reactants. So energy has been released to the surroundings would be a lovely thing to add on the end of that. All right, for the reaction, the value of A is 1370. The value of A is 1370. And C is 3230. Okay, calculate the value of B. So they're telling you that you've got to put this much energy in, 1370, and this much energy is released, 3220, so that 3230. So the difference between these two values, right, well, what you need to do is you go 1370 minus 3230, and you will get the answer of 1860 kilojoules, and that will be it should be a negative value. You should really write the negative value in there. It wasn't on the mark scheme as being a negative value, but it's an exothermic reaction. I just realised that all of that was off the page. I wasn't focused. Right, everybody, pretend that didn't happen and just tell everybody that I never make mistakes. All right, so it's 1370 minus 3230. So the difference is minus 1860. You didn't see anything there. Yeah, he's brilliant, Dr. Norton. He always gets stuff right. He's so slick. Right, alcohols are used as fuels. They are. You can set fire to alcohols and they burn really, really well. If you've ever done a D&V camping trip and you've used a Trangia stove, you're burning methanol, typically. Oh yeah, was it methanol? Yeah, let's go with that. You can burn ethanol on your Christmas pud. Alcohol, okay? But you can use, they're really, really good fuels. You can put ethanol in cars. They use ethanol as a fuel in Brazil, all right, because they haven't got much crude oil of their own, so they so instead of buying in loads of petrol, in Brazil they use alcohol or ethanol inside their car engines. A group of students investigated the amount of energy released when different alcohols are burned. I'd love to do this experiment with you, but on lockdown we can't. The students use the apparatus shown in figure 2, so you get a little burner there with some alcohol, and you've got a little flame going on. And so what they're saying is the heat released from this burning, they're trying to capture the heat in some water. So they're seeing how much the flame heats up the water. So figure 3 shows the start temperature and the final temperature of the water. You get a few things like this where you've got to read apparatus on a piece of paper. Okay. So what you do here, well, that's 22 and that's 23. So this value is going to be 22 point something. You look at the scale, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 22.5. Then 37, 38, 39. So this is 38 and 39. It's 38 point something. 5, 6, 7, 38.7. Start temperature is 22 point. I'm off the page again. 22.5. Final temperature is 38.7. 16.2. Foundation level stuff. It is genuinely. Okay, that's not hard. It's exothermic because it's releasing heat to the surroundings. All right, next. The equation for the reaction of ethene and bromine. Now, again, you do a little bit more on this. Ethene's a cool chemical. Looks like that. Ethene, you can react loads of these ethenes together to form polyethene, which literally means many ethenes joined together, like polythene bags, okay, plastic bags. Ethene reacts with bromine to make this thing called 1,2-dibromoethane. The reaction is exothermic, so it releases heat. Heat exits, thermal energy exits. Complete the energy level diagram. Well, it's exothermic, so first thing you just choose a line. Don't worry about scale on these, there isn't meant to be one. You just draw it lower. Complete the energy level diagram. You should label the activation energy. Well, first I'm going to do this because they've done the reactants, so I may as well draw the products. So completing it means you draw your loopy-doo, your activation energy curve. You should label the activation energy, so I'm going to label it from here to here. Remember what I said, that arrow's got a touch up there, you know. Activation energy, so I might... Activation energy, all right, and enthalpy change. Let's go into that line, delta H. Right, what are the marks for? Energy, activation energy drawn and labelled. Products are at a lower energy and delta H correctly labelled. Cool, right, the equation for the reaction can be represented as this. Use the bond dissociation energies. The word dissociation means to break apart. So if you've heard of the word association, if you associate with someone, you come together with them. All right. So an association, or it means a coming together. Dissociation is the opposite. It means to break apart. So I'm going to dissociate myself from my friends. Would mean I'm going to break up with my friends. I'm not going to go and see them again. So when bonds dissociate, they break. So they're known as bond dissociation energies, or so hopefully that makes sense. You might not have known what that word meant. Use the bond dissociation energies in the table to calculate the enthalpy change for this reaction. Okay, so what am I doing now? I've only given you that much space. All right, so boom, draw a line down the middle. It's going to be messy, this. I'm going to do the bonds broken on this side and the bonds made on this side. So I'm going to do 1, 2, 3, 4. There are 4 CH bonds, 4 times CH, which is 4 times 413. So that's them. I've got a C double bond C, C double bond C, and that is 614. And I've got a BR. Right, BR 193. And what I've got to do is add them up. I'm going to be a little bit lazy, and I'm going to go with, I'm going to just look up the answer. 2459. 2459. I'm going to tell you what they did on the mark scheme in a minute. They took a nice little shortcut on the mark scheme. But this is the amount of energy you need to break all of those bonds. You're making bonds. I'll just use a different colour. You don't have to use a different colour in the exam. 1, 2, 3, 4 CHs. So you're going to make 4 CHs. Now, this is what they did on the mark scheme. They said, well, if students realise if you're breaking 4 CHs and making 4 CHs, you don't actually need to do the 4 times 413 bit. But I'm going to do it anyway. All right. But clearly that and that will cancel each other out. Anyway, I've got a C single bond C, which is 348. And a CBr and a CBr. CBr times 2. 2 CBRs is 2 times 276. Plug them in, add them up. What's that going to be? 2552. 2552. All right, if I look at these two values now, more energy is released making bonds than is taken in breaking bonds. Now, I'm not being slow down, you have to think that through. B in, B out. More energy is given out making bonds than taken in breaking bonds. Okay. Final bit of the calculation is the first number, 2459 minus 2552 equals minus 93. But I bet some of you didn't get that right. And it's not because you don't understand the question, it's just because you'll have made a little mistake with a number. You might have written 431, in which case you'll be miles out with your answer. You see what I mean? It's quite easy to make mistakes. So I get it. Having made many mistakes on these in front of classes, I fully understand. All right. Part 2 of that then. Oh, right. Oh, that's... Oh, no. No, where am I at? Question 2. Back page. That was here. That was where I was meant to work it out. The reaction is exothermic. Aha! So here's my bit. Now, this is what the last video was about. It was about the B in, B out. Now, I reckon, right, that a lot of you won't have done this particularly well. The reaction is exothermic. Explain why in terms of bond broken and bond formed. So why is it exothermic? Because more energy... So I draw this, BB in, MB out, to help me. More energy is given out making bonds than is taken in breaking bonds. Look at my fantastic handwriting. All right. That's how you do it. Just watch that question. That question will always catch you out. If you're the person who's taking the time to know how to answer this question, you're going to smash this. Okay, question 3. This question is about energy change in the chemical reactions. Balance the chemical equation. Right. 1 carbon, 4 hydrogens, 2 hydrogens. Hydrogens are balanced. Oxygens, 2 oxygens, 1, 2, 3, 4 oxygens. Done. Next. Where are you? He's so organised. No, he's not. Where's B? Well, I have totally lost. Oh no, just go straight into C. That's why. Right, the chemical equation for the combustion of ethanol is this. There's ethanol doing that. Combustion means burning. It's going to be exothermic. Because remember, you had to learn examples of exothermic and endothermic. The equation for the reaction can be shown as... Now, I've added this bit and this bit on. I hope you realise that you don't get them in the exam. Right, use bond energies to calculate the overall change. Right, how many bonds am I going to break? I might even split it up like this. Bonds broken, bonds made, or making bonds. Okay, 1, 2, 3, 4, 5. 5 CHs, 5 times CH, which is 5 lots of 413. Boom, CC. 347. CO. 358. And OH. 467. Alright, bonds. Oh man, I haven't finished. 3 O double bond O's. So that's O double bond O. 3 lots of them. 3 times 495. Nearly mucked up there, didn't I? Add all them up. It's a whole lot of bonds. 5998. Alright, so there's loads of places you can muck up there. God, I went off the page again. Alright, I nearly forgot my oxygens, in case you didn't work out what was happening there. 3 lots of oxygen. Making bonds. There we go, I'll keep it all on one page. You got 2 lots of this, so that actually means, in essence, you've got this, yeah? So, 1, 2, 3, 4. 4 lots of C double bond though. 3 H2Os. If I draw it out and better for you, means that 1, 2, 3, 4, 5, 6 OH bonds. 4 C double bond those. 4 times 799 and 6 times 467. Oh, I did my calcs wrong. Hang on. this side wasn't 5998, this side was 4722. I'm totally mucking up this video enough for you. And this is 5998. Alright. Anyway, that's how you do it. So I hope this sort of idea was useful, showing you the bonds made, showing you how to lay it out, showing you how to miss bonds off on purpose. No, don't do what I did. Alright, then you do 4722 minus 5998. And the answer is minus 1276. Minus means exo. It says on the mark scheme you can ignore the plus or the minus. I don't want to ignore that. You guys are so good at chemistry. If it's exothermic, this number minus this number will give you 1276. Alright, minus 1276. So the minus tells me it's exo. This reaction is exothermic. Explain why in terms of bonds broken and bonds formed. Alright, exo is that. B in, MB out. Alright, because more energy is given out making bonds than is taken in breaking bonds. Yay! I'm a champ. Right. Nearly there. Complete the energy level diagram for the combustion of ethanol. Combustion is exo. Combustion, exo, activation energy. Activation energy, energy change, delta H. Again, take it to the line there. And I'd write, maybe down here, I'd write 2CO2, 3H2O down there. The equation can also be written, this is sort of question 4, so there's a missing part of question 4. So it's just another calc to do. Watch out with this one. 2 lots of this. So 1, 2, 3, 4, and then 2 lots, 5, 6, 7, 8. 8 CH bonds would have to be broken. And OO would have to be broken, so that's 8 times 435. And O double bond O, 497, that's everything there. Add them up, that'll give you that answer. Energy required to break bonds. And it's 2 lots of this, 1, 2, 3. So that's going to be 4, 5, 6. 6 CHs, CO, and an OH. 6 CHs is 6 times 435. A CO is 336 and OH is 464. Add them together, plug them into your calc. This minus this, you got your answer. Alright. I am tired. I am done. Right, next week I'm going to see I'll probably send out some more work next week, but not loads. Just more of these sort of calcs. I hope that's alright. Including these sort of challenge ones where they give you a missing bond enthalpy. I hope you're enjoying looking at this blank piece of paper. I'll put a crayon there. Right, see you next week. Take care of yourselves. Goodbye.